The objective of this video is to use small signal analysis to drive the transfer function of a power converter for regulator design. So we've been building up our tools for regulator design, and in our previous videos we talked about other components of our loop transfer function, including the regulator, our negative feedback factor, but we left as question marks our power converter model and our regulator design. So in this video, we're going to talk about first the model for a power converter, how we develop a small signal model to represent the power converter as a transfer function. And then we're going to provide, towards the end of this lecture, an example of how you might design a regulator to control your power converter. But in order to get there, we're going to have to develop a small signal model for a power converter. And so the first question is, why do we need to develop a small signal model? Well, the answer is that if you're considering purely static situations for your duty cycle, so if D is constant, you don't need to worry about a small signal model because your converter is linear. However, in dynamics, you have D as a function of time, so your duty ratio is a function of time, and so are your pole current and your throw voltage. And this creates nonlinearity in our system. So when we go to analyze circuits, linearity and superposition are fundamental to the tools that we use for circuit analysis. And when we have d of t times I p of t for our current source, and d of t times vt of t, we can see that this principle is violated. So with superposition, we know that we can solve our circuit with some sources off and other sources on, and then solve the circuit again with the sources that were on being off and the sources that were off being on, and then sum the results. So it's a common practice for solving a system with a bunch of sources to turn one source on at a time, solve for your currents, and then sum up all the results to get your final currents in your system. But if we were to do that here, if we were to set d of t equal to 0, we can see that immediately this entire current source has to be 0. It doesn't matter what IP is. And likewise, if we set IP of t to be 0, then it doesn't matter what d of t is, this current source is off. So the whole system collapses when we have this nonlinearity. And the nonlinearity arises because we have these quantities that are multiplied by each other, these time-varying quantities that are multiplied by each other. So we lose our linearity and we lose our superposition. So what should we do? Well, we can use the Taylor series to linearize a set of equations. This is something that you learned from your multivariable calculus class, but maybe have since forgotten, so we'll provide a brief review of this. And the Taylor series tells us that if we were to have some kind of arbitrary function f of x that maybe looks like this, clearly it's nonlinear. The Taylor series builds upon the idea that we could pick some point on this circuit, and if we zoom in close enough, we can approximate a region of the circuit as of the line as a straight line. So we've got this nonlinear characteristic between f of x and x, and if we pick a point right here, we zoom in close enough, we can approximate the relationship as a linear relationship, as a straight line. And this property holds for only small changes in x. It wouldn't do us any good to use our straight line about a point over here. But for some for some small variations in f of x and some small variations of x, we can fairly accurately model this as a linear relationship about a bias point. So our bias point was the point that we chose to calculate the slope of the line at. Formally, our Taylor series can be written as, our Taylor series for a two-variable system, f of x, y. And why are we looking at for two variables? Because in our circuit up here, our current source and our voltage source are a function of two variables. Our current source is a function of our duty ratio and our pole current, and our voltage source is a function of our duty ratio and our throw voltage. So if we look at the Taylor series expansion for a two-variable expression about a bias point of AB, we find that it can be expressed as follows. And these are just the first set of terms in the Taylor series. It goes on to use higher order derivatives. But if we stop the series at this first set of terms, if we say this is approximately equal to this first set of terms here, we have a linear relationship. This quantity right here is our partial derivative of our function with respect to our first variable, and then evaluated at the point a, b. So we can say that this is the partial of f with respect to x evaluated at our operating point. And similarly, this is the partial derivative of our function with respect to the y variable, and again evaluated at the operating point. So in our system, x is equal to our duty ratio, and b is, or y is equal to either our pole current or our throw voltage, depending if you're talking about the voltage source or the current source. And so we can write this out for our system. We can say that in our system we have F1 of D and our throw voltage is equal to the function evaluated at a nominal operating point. And I'll use capital letters for this. This term right here would be, we're specifically talking about the voltage source at this point, and this term right here is going to be our duty ratio times our throw voltage. It's the original expression, but using capital letters to indicate that this is the nominal point. This is the operating point that we're considering our circuit to be linearized about. This is this coordinate right here. So this would be the operating point, or the bias point. And then we add to that little d minus our operating duty ratio times the partial of F1 with respect to the duty ratio and evaluated at our operating point, which in this case is going to simply be Vt. So this is equal to dF1 evaluated at dVt with respect to d. And then we can do the same thing for our second term. And then we have these higher order terms which we're going to neglect. We're going to neglect them because we want to have only the linear terms. We want just our linear approximation. And similarly, capital D is the partial derivative of F1 evaluated at d and Vt with respect to Vt. So we can note that this first term is our nominal point, or our bias point, or operating point, or nominal operating point. We can label this second term as being d tilde, because it is going to be the small signal perturbation about our operating point. And the next term we can label as v tilde, because again, that will be our small signal perturbation. So both of these points are our small signal perturbation. And we can finally rewrite this equation as being alright, and now we can write the same expression out, or we can do the same thing to evaluate the Taylor series of F2, or our current source. And if we do that, we'll get the following expression, where capital IP is simply the partial derivative of F2 with respect to D, and capital D is the partial derivative of F2 with respect to IP. So we have these two expressions which we can use to construct our small signal circuit. And the way that this works when you draw a small signal circuit is that you take out any DC terms. So these first two terms right here are the DC, or operating point terms. And we remove those from the circuit that we're studying because we assume that that is studied separately. We want to be able to add the results of our small signal circuit to our DC equivalent circuit to construct our final system. So our small signal circuit is going to consist strictly of these two terms and these two terms. So let's now sketch what the circuit will look like. We're going to replace each of the sources with its linearized model from the Taylor series. And the first source that we have on the leftmost is actually our throw voltage, and we'll sketch it just as a small signal perturbation. We're going to again turn off the DC component of it, so we'll model this as an AC, a small signal AC source. And then for the current source on the top, you can see that we have two terms on the right. F2 has two terms, d tilde times capital IP and capital D times I tilde. And the way that you add current sources is that you place them in parallel. So we'll draw two current sources in parallel. And then going out here, we again have our inductor, and we have our resistor. On the bottom, our equation F1 also has two terms. So the way that you add two voltage sources is that you place them in series. And we now have a complete circuit that we can study to extract transfer functions. So now we have a linear circuit where all of our sources consist of only one time varying quantity. We can vary either any of the tilde terms. All of the capital letter terms correspond to our bias point or nominal DC circuit operating point. And so what we're interested in doing in this lecture is deriving the relationship between D tilde and V out tilde. So we want to derive the relationship between our small signal output voltage and our small signal duty ratio. So now let's go for deriving our relationship. And to do this, we're going to set Vt tilde equal to 0. We can do this because we can change the value of any source. So we're allowed to set this to 0. However, we cannot set Ip tilde to 0 because that's not a source. That's actually a variable in our circuit that we have to solve for. So let's redraw our circuit now with Vt tilde equal to 0. So notice that by setting V tilde t to be 0, we've removed two sources from our circuit. We removed both this source up here and this source over here. Now, we want to express our output voltage in terms of our duty ratio, and this is pretty simple because we know what our throw voltage is. So we say that V out tilde is equal to D tilde times Vt, so this voltage source right here, times a voltage divider. So times R over R plus SL. And to get our transfer function, we just divide both sides by D tilde. So we end up with V tilde of S over D of S equal to this simple expression. And this is our transfer function. So this is the transfer function that fits into the loop transfer function that we've spent the last couple of videos discussing. So let's draw how that fits in. Now we can show our transfer function for our small signal model as being V0 tilde star, which goes into a regulator block that we still don't know. This is a question mark, regulator. And that generates a control voltage, which is now a small signal control voltage. And that connects to our PWM block that has the gain of 1 over V peak that we talked about last time. And now this creates d tilde, which feeds into our model for the converter. And we have a feedback path times our negative feedback factor, or sensor gain, beta. And so again, what we've done is we've populated this block that was an unknown for us last time. And you can see that this block depends on the passive components that you've connected to your converter. So it's the linearization about the operating point that was required to convert our throw voltage to our nominal output voltage. And using that operating point, you could calculate your nominal duty ratio in order to make that happen. And then we used our Taylor series approximation to construct a small signal circuit and derive this transfer function. Let's now make this a little more concrete by discussing an example. And we're going to develop this example to the point of designing a simple regulator transfer function. And so you should recognize this as a simple buck converter. And if this buck converter is operating at this point, we can recognize that it must have a nominal duty ratio of 10%, because 100 volts over 1,000 volts is equal to 0.1. And in this problem, we're going to assume that V peak, which is the peak value of our triangular waveform PWM carrier, is equal to 10 volts. And this means that we must have a gain for it of 1 over V peak, which is equal to 1/10, which is equal to 0.1, which is in fact equal to negative 20 decibels. So we can sketch the block diagram of our control loop. It's having a regulator, having our PWM stage, which we just noted is equal to negative 20 decibels, going into the model of our converter. To analyze this further, we need to specify what we want our input voltage reference to appear as in order to get the 100 volt output. And let's say that we want V out star to be equal to 1 volt, which is going to map to our 100 volt output. And this means that beta is equal to 1 volt over 100 volts, which is equal to 0.01 or negative 40 decibels. So we're writing these gains in terms of decibels because we're going to go to a frequency, a Bode plot analysis shortly. So right here we have a negative 40 decibel gain. We've already remarked that Vt is 1,000 volts, which is equal to 60 decibels. So we can see that in our transfer function for our converter, we have 60 decibels times the remaining terms of our transfer function. We can note that this is 60 decibel volts, and we have 100 ohms, which is going to be 40 decibel ohms. And so we can observe from this that in fact negative 20 decibels here and negative 40 decibels here will cancel out our 60 decibel gain in the transfer function for our converter. So we can simply we can start by plotting the transfer function for the converter by neglecting the Vt term. And let's do this. Let's go ahead and start plotting that transfer function as a Bode plot. And we can start, so the transfer function that we're going to work towards plotting here is the transfer function of R over R plus Ls. And we had noted that R is equal to 100 ohms, which is 40 decibels, and L is equal to 1.54 millihenry. And we're going to do this not by using mathematical techniques. We're going to do this strictly using the graphical approach that we've discussed in our previous video. So let's start by plotting R on here. Plot R as a red line, and it's 40 decibels, which means it's just going to have a constant magnitude with respect to frequency at 40 decibels. And its gain, or its phase angle, is going to be a constant 0 degrees over all frequency. Next, we'll plot LS. And I picked L to be this magic number 1.54 because that corresponds approximately to pi over 2. The gain of the transfer function LS is equal to pi over 2 times 10 to the 3, because it's milli, times 2 pi f, which ends up being pi squared f over 10 to the 3, or f over 100. So we can plot the gain of that, simple enough. It's going to have a crossover. It's going to cross over the 0 dB line at 100 hertz. And a decade later, it's going to have a value of 10, which is 20 decibels. And a decade earlier, it's going to have a value of 0.1, which is negative 20 decibels. And so it's going to be this straight line. And the entire time, it's going to have a phase angle of 90 degrees. So now we're going to add R plus R and LS. And when we do the addition, remember we're taking the maximum magnitude along the whole track. So we've got a Bode plot of LS, we've got a Bode plot of R. So we can take the maximum magnitude along this entire path, which is going to look like this. It's going to be the same value as R until we get to this inflection point, this crossover point here, and then it is going to take the LS trajectory. And the phase angle of this in the low frequency regime is going to be the angle of R, and at the point that the frequencies cross over, so this is actually supposed to be, this point right here is actually 10 kilohertz if I draw my line straight. At that point, we're going to have the average between the two phase angles. That means we're going to have 45 degrees at this point. A decade earlier, we're going to have 0 degrees, and a decade later, we're going to have 90 degrees. So our phase angle plot is going to look like this, where this is the argument of R plus LS. So we use that addition operator that we talked about in our previous video. Now, we're going to take R divided by R plus LS. So when we divide two transfer functions, we subtract them. That's what we learned about in our previous video. And so if you subtract, we're going to subtract this purple curve up here from this red curve. And if you do that, let's show it in green, you're going to end up with 0 decibels along this trajectory here. And then at 10 kilohertz at this point, it's going to start to trend downwards at a rate of 20 decibels per decade. And similar with our phase angle, we're going to track this trajectory here, and then at 1 kilohertz, we're going to start to go downwards, so we'll get to negative 45 degrees at 10 kilohertz and negative 90 at 100 kilohertz. And so finally, we have the Bode plot for our transfer function of our power converter, normalized by a VT, of course. Remember, we canceled VT out. So we now want to design the regulator for our transfer function. And remember the design guidelines we talked about in our previous video. We want to cross over the 0 decibel point at a slope of negative 20 decibels per decade. So right now the slope of this line is negative 20 decibels per decade. And we also want to have a very high gain at low frequencies. So right now you can see that currently we have a rather low gain, but we'd like to have a high gain. And so what we can do to accomplish this is we could imagine that we could have a transfer function that behaves like this for the regulator. Remember that the regulator transfer function is going to be added to the transfer function for the power converter. And so we could imagine that we could have our regulator behave something like this, where it comes down at a rate of negative 20 decibels per decade. And if we were to continue that line, if we were to continue this hashed brown line at the same rate, we'd be in trouble because we'd be crossing over right here at negative 40 decibels per decade. So what we could do is we could then have this line start trending flat to the right. And if we did that, if we had this transfer function, the brown line for our regulator, added to the transfer function for the power stage, the green line, you can see that we'd have the performance that we'd want. We'd have a high gain at low frequencies. We'd cross over the 0 decibel point at negative 20 decibels per decade. And so we'd follow the design guidelines that we talked about in our last lecture. We'd also end up with presumably a good phase margin as well. And so what is this transfer function composed of? This fictitious transfer function that slopes down at negative 20 decibels per decade and then goes off to infinity with a flat gain. Well, we can view it as being the addition of two terms. One term that's going off at negative 20 decibels per decade and has a gain of 1 when we get to 10 kilohertz. So this can be 2 pi times 10 kilohertz over s. That would give us the transfer function in this region here. And if we were to add that term to a transfer function that has a constant gain of 0 decibels, that is, it has a constant gain of 1, we would get the behavior that we've shown here. So if we write this out, we could say that g of r is equal to 1 plus 2 pi over s. Or in other words, 1 plus omega z over s. We have an inverted 0. This is the form of a PI regulator. In this case, our proportional term has a gain of 1, and our integrator term has a gain of omega z. So this is an inverted 0, and it also happens to be the transfer function of a PI regulator. So if you didn't know what you were doing, if we hadn't done this Bode plot analysis, you might have guessed that you'd want to use a PI regulator because PI regulators are pretty standard, but you wouldn't have known where to put your zero location. You wouldn't have known what gains to put. You could have accidentally chosen to have omega z be very large, and then you would have ended up with some hypothetical transfer function that did this, and you would have been in trouble. So if you had designed your transfer function to behave as I just drew, as this hash line here, where you cross over at some really high frequency, suddenly when you add this line to your green line, you're going to see that you're going to cross over with a gain of negative 40 decibels per decade, and this will have a phase margin of 0 degrees. It's actually going to give you, it will result in instability. You'll have a negative 180 degrees phase angle. And you can easily convince yourself of this by plotting the phase angle of your PI regulator, or your inverted 0. It's going to be negative 90 degrees in the low frequency region. And then a decade below, it crosses over the 0 dB line. It's going to start increasing. It'll be 45 degrees at the 0 dB line. And then 90 degrees a decade later. So when you add the green line, your regulator line, or your power converter transfer function, to your regulator transfer function, you'll see that you'll end up crossing over somewhere around here. And if you add the phase angle of the green line with the purple line, you're going to end up getting negative 180 degrees. So if we show down below what our phase angle is going to be for this final loop transfer function, it would be something like this. So right here we start to decrease as we're adding our two transfer functions. We get to negative 180 degrees. And this is where we go unstable, because this is the gain crossover point, or the GCF frequency. So in other words, our phase inversion frequency is occurring at a lower frequency below our GCF frequency if we pick omega z to be too large. So this shows you how you're able to go from your equivalent circuit of your power module, or your power converter, to drive a transfer function, a small signal transfer function for your converter. How then, instead of using algebraic operations, you're actually able to use graphical techniques to plot the frequency response of it, and how that can inform the design of the PI regulator, or whatever regulator you choose to use, in order to obtain a desired loop transfer function. And our techniques for designing regulators, and for in fact realizing the transfer functions of the regulators, will be developed more in further videos.